Hey everyone, it's Mr. Canfield, doing my home video. So today we're going to look at definite integrals with u-substitution. Just in case you're missing the subtlety here, I read the title. All right, so the big deal here is when we have an integral like go from 0 to, let's use the other marker. Restart the video. No, all right, we'll go from 0 to 2x times x squared plus 1 to the third dx. The issue is these bounds are x values. So one way for us to do this integral, it says without changing limits. This is, for this problem, this is actually really obnoxious. So, I was thinking, like, one way we could do this is we could cube this out, distribute the 2x, and then integrate, and then go for, and do 0 and 2. But Stu might be meaning, hey, take this, and we'll do our traditional u-substitution where usually the stuff on, the further inside is usually our u. So I'll say u is equal to x squared plus 1. And so if I find my du dx, then that's going to be 2x. So that means that du is equal to 2x dx. And so dx is just equal to du over 2x. So with that in mind, I thought I had more colors. I'm limited, my color palette's limited to black and other black right now. I think I know where they are. Anyway, so what I can do is put du over 2x where dx is. And so if I do that, I can put this, I can put u in that place. And then I can put du over 2x in dx's place. And then we can see that the 2x and the 2x cancel. And so now we're left with the integral from 0 to 2 of u cubed du. The problem is, and this is an issue right here. People get confused and they go, oh, the 2 and the 0, we'll just plug them in at the end. But the thing is, this is an x value, this is an x value, this is a u value. One of my favorite little phrases to make here is that u and your x don't mix. I think I said that in my previous video. And it's a silly thing, but it's just to remind you that this 0 and 2 right now are kind of meaningless to us. And if we just kind of keep them there, then we can, as we go, we'll integrate this. Integral symbol's gone. We'll integrate this. We'll get u to the 4th over 4 evaluated from 0 to 2, but not really from 0 to 2. We'll evaluate it. We'll go, now I need to plug back in the x squared plus 1 to the 4th over 4. And now I can go from 0 to 2. So this would be the only way that we really have to do this. But there's a way to do it where we change the bounds. And so what that looks like, the main difference here is, you know how normally we go through and we want to make sure there's nothing that's x that's left over? Well, the big difference, the big thing that we do differently is at this point where we have u cubed du. So let me start there. U cubed du. Well, our top bound here, our upper bound was x is equal to 2. Oh, Maeve's trying to help. Our bottom bound is x is equal to 0. So all we have to do is go, well, when x is equal to 2, I can replace this with a u value, knowing that u is equal to x squared plus 1. So I could say, well, that means that u is equal to 2 squared plus 1, or 4 plus 1. U is equal to 5. So that x was a 2, but now the u value there is a 5. And when x is 0, same kind of thing. U is equal to 0 squared plus 1, 1. So now the benefit of this, when we do our integral, we get u to the 4th over 4, evaluated from 1 to 5. I can just plug in that 5 and that 1 now. Get 5 to the 4th over 4 minus 1 to the 4th over 4. And we're actually done there. So essentially what we did was we plugged in the 2 and we plugged in the 0 to this, but we did it at a slightly different point in time. This is a really powerful technique. And by powerful, I think I mean there's usually an AP question where it'll give you something where we wind up doing u-substitution. It says, which one of these is equivalent to this original integral? So like they give you this integral, and then one of the answer choices would be 1 to 5 u cubed to u. Oh, God bless you. So that's what's going on with these things. So I'm not going to do it without changing limits anymore, because the whole purpose of this section is for us to kind of get that technique down. All right, so our next example, I really think for this whole section, I could just focus on how do we change the bounds, but I'll be more professional than that. All right, so she's like, what are you doing? Why aren't you looking at me? All right. So if we go far inside here, we have the 1 minus x squared. So we can say u is equal to 1 minus x squared. And so then our du would be negative 2x dx. So skipping steps a little bit. So I could say that's negative du over 2x is equal to our dx. So if we go in here, oh, you know what? Something else. Let me actually change the 0 and the 1 now. Since we're changing everything into u's, let's change those into u's. So if x is 1, then we could say u is equal to 1 minus 1 squared. Oh, that's just 0. Okay. And then if x is 0, that's 1 minus 0 squared, and that's 1. Okay. So even though these numbers are kind of funny, that's okay. It just means that we're going to end up with an answer. We're going to wind up plugging in 0 first minus plugging in 1. And that's perfectly okay. If that's bothering you, remember, you can always switch those bounds and throw a negative out front. Okay, so when I go through and do my u-substitution, I still have my x. Instead of writing the square root, I'm going to write the 1/2 power, because that's the same thing. We got our u in there, and then instead of writing dx, I will write my negative du over 2x. So now when I look, all right, so I see my x's are going to cancel. I'll throw the negative out front. So it looks like we got negative. You know, if I just thought a little bit more ahead, some of these things will come out in the wash naturally. The ones here, the zeros here. All right, so I'm gonna definitely do I'm gonna do a little trick here. Oh, there's an over 2, so I'm gonna have actually a negative 1/2 out front. Okay. So it's negative 1/2, and then it goes from 1 to 0. Well, let's flip the bounds. You don't have to do this. You could totally just integrate this as it is right now. Oh, forgot the du. But let's flip the bounds and pull the negative out. So 1/2. Ooh, God bless you. She sneezes a lot. You know, it makes it just a little bit nicer. Also, I have trouble with the top of my integrals. They kind of flop over. All right. So 1/2 parentheses. So we'll add 1 to the exponent, right? U to the 3/2 divide by our new exponent. So instead of writing over 2/3, instead of writing over 3/2, we write times the reciprocal, evaluated from 0 to 1. So winds up looking pretty nice in the end. And little side story about my life. Calculus was the class for me where I was like, oh, fractions aren't that bad. Like, they're ugly, but it's more annoying than anything else. So I'm going to finish this because it winds up being nice in the end. So I wind up getting 1/2 times 2/3. The 2's cancel, we get 1/3. And then this is 0, so the answer is just 1/3. So, fun. All right. What does this get into? So 3 is more of the same. I'm gonna skip the, yeah, it's just, so if we just talk about 3 for a second, the thing that, I'm not gonna do the whole problem, but the point that's worth talking about here, and again, if you do the problem and you have a question, feel free to ask me. The thing that's worth talking about here is when we plug in pi over 4 and 0 into this sine of 2x, or like when we wind up doing u-substitution, it's going to change these a little bit, but in the end, those pi's and stuff all disappear. So the bounds are, this bound is still going to have some pi in it, but that's fine. Yeah. So 4 is more of the same. 5. There is no number 5. I've not seen this. That's amazing. And see, this is why I shouldn't do these before. I should just do these blind, because that you got the genuine reaction. That's incredible. Okay, I want to look at this one down here. It says if the integral from 0 to 1 of f of x dx is 6, and from 0 to 2 is 4, and from 0 to 4 is negative 8, so yeah, this is a different way for us to think about this. So remember, if we have f of x, capital F of x, then we can say capital F prime is equal to regular f of x. And so that means that the integral of regular f of x dx is equal to capital F of x plus c. I guess there'd be a dx on here, but the main idea that I want to drive home is that I'm going to use this capital notation. That's part of the fundamental theorem of calculus, but just to reiterate. So in this situation, we have the integral of f. I wrote it wrong. Someone's got the growls. we've got f of 2x dx. So, where did I put her toy? So when we've got, when we say u is equal to 2x, that's really what we're going to be thinking about here. Then that means that du is equal to 2 dx. And so we'll divide both sides by 2, get the over 2 right there, and we'll be able to say that this is 1/2 f of u du. And all we need to do now is make sure that the bounds match up and we're good. So the bounds go from 0 to 2 in the original. Well, remember that u is equal to 2x. So that means that u is equal to 2 times 2 for the 2, and we get 4. And then u is equal to 2 times the 0, and we get 0. And so now I can go look at my different options. Oh, from 0 to 4, f of x dx is -8. So this is just 1/2 times -8, or -4. And I want to remind you, so you might be like, well, these are u's and those are x's. Just remember that these are dummy variables here. This could be f of t dt. This could be f of m dm if we're going to pick on Maeve, or f of j dj if we're going to pick on j. So it's just, once we change this into u's, if we change those bounds, boom, there we go. So it's kind of a subtle shift on what we've been doing. So that's going to be my abbreviated lesson for this. I hope it was helpful. If it wasn't, obviously, please let me know. Please let me know how I can be helpful. And let's just one more time. Hey, Maeve. Hey, Maeve. Hey. Maeve. Hey. Hey, you. Hey, you. Hey, you. Now she doesn't want to look at me. She's been looking at me the whole time. So she's almost 6 months old, and she's able to grab things, which, like, stuff that's so basic to us, like just picking things up. You have to learn how to do it. So she used to get her hand caught in this all the time. She still probably will get her hand caught. Also, she likes to eat everything. I'm not doing any more math this video. Here, let's flip her. What you doing? I'm just making silly faces at her. Oh. So, see that blue line? That tells me it's time to change the diaper. All right. Bye.